Welcome and introduction to ECDHE. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into ECDHE, elliptic curve Diffie-Hellman ephemeral. This might sound like a mouthful, but I promise you'll understand not just what it is, but why it's the gold standard for secure key exchange in modern cryptography. ECDHE is the technology protecting your online banking, your WhatsApp messages, and virtually every secure connection you make on the internet today. It combines three powerful concepts: elliptic curves for efficiency, Diffie-Hellman for key exchange, and ephemeral keys for perfect forward secrecy. Think of ECDHE as the evolution of the classic Diffie-Hellman algorithm we have discussed before. If traditional Diffie-Hellman is like using a massive padlock, ECDHE is like using a sleek, modern smart lock that is not only more secure but also faster and uses less battery power. This efficiency is crucial in our mobile-first world where every millisecond and every bit of battery life counts. By the end of this presentation, you will understand why major tech companies like Google, Microsoft, and Apple have made ECDHE their preferred choice for secure communications, and why it is considered essential for modern web security. Evolution from classic Diffie-Hellman. To truly appreciate ECDHE, we need to understand the journey from classic Diffie-Hellman to where we are today. This evolution was not just about making things better, but it was driven by real-world constraints and threats. Classic Diffie-Hellman, invented in 1976, uses modular arithmetic with large prime numbers. To achieve adequate security today, we need prime numbers that are at least 2048 bits long. For long-term security, 3072 or 4096 bits are recommended. These massive numbers mean slower computations and more data to transmit. Imagine trying to send a 4096-bit number over a mobile connection every time you connect to a website. The computational cost is significant. On a modern processor, a 3072-bit Diffie-Hellman operation might take 10 to 20 milliseconds. That doesn't sound like much, but when you're handling thousands of connections per second on a web server, or trying to preserve battery life on a smartphone, every millisecond matters. Enter elliptic curves. In 1985, Neil Koblitz and Victor Miller independently proposed using elliptic curves for cryptography. The breakthrough insight was that elliptic curve mathematics could provide the same security level with much smaller numbers. A 256-bit elliptic curve key provides roughly the same security as a 3072-bit RSA or Diffie-Hellman key. That's a 12x reduction in key size. But why stop there? The ephemeral part of ECDHE addresses another critical issue: perfect forward secrecy. With static keys, if an attacker ever compromises your private key, they can decrypt all past communications. Ephemeral keys are generated fresh for each session and then discarded, ensuring that even if a key is compromised, past communications remain secure. This is like changing the locks on your door after every visitor. Extreme, but incredibly secure. Understanding elliptic curves. Let me explain elliptic curves in a way that actually makes sense. Forget the complex math for a moment. I'll give you the intuition first. Imagine you have a special kind of clock, but instead of going from 1 to 12, it has millions of positions. And instead of moving in a circle, it moves along a weird, curvy path that loops around in a very specific way. This curvy path is our elliptic curve. Now here's the magic. On this special clock, we can define a way to add positions. If you're at position A and I tell you to add position B, there's a rule that tells you exactly where you'll end up. Let's call it position C. It's like having a treasure map where combining two locations always gives you a third specific location. Here's the brilliant part. If I put you at a starting position and tell you to keep adding that same position to itself 1,000 times, like going around the clock, you will end up at some final position. But here's the kicker. If I show someone else only your starting point and ending point, they have no efficient way to figure out that you went around exactly 1,000 times. They would have to try every possible number. Did you go around 1 time? 2 times? 3 times? 999 times? 1,000 times? With the huge numbers we use in real cryptography, this trial and error approach would take billions of years. This is completely different from regular multiplication. If I tell you 5 times 1,000 equals 5,000, you can easily figure out that I multiplied by 1,000 just by dividing. 5,000 divided by 5 equals 1,000. But with elliptic curves, there is no such division shortcut. It is a one-way street. Easy to go forward, nearly impossible to go backward. The curves we use have names like P256 or curve 25519. The numbers indicate the size of the curve. Bigger curves are more secure, but they are also slower. P256 is like having a clock with 2 to the power of 256 positions. Even if you could check 1 trillion positions per second, it would take longer than the age of the universe to check them all. The beauty of elliptic curves is that they give us this one-way property with relatively small numbers. While traditional methods might need thousands of digit numbers to be secure, elliptic curves can be secure with just 77-digit numbers. It's like getting a bank vault's security in a package small enough to fit on your phone. How ECDHE works step by step. Let me walk you through exactly how ECDHE works using a simple analogy that will make the math crystal clear. Imagine you and a friend want to create a shared secret color, but you can only exchange colors through a public bulletin board that everyone can see. Step 1. Agree on the starting point. First, you and your friend agree on a base color. Let's say yellow. In ECDHE, this is like agreeing on a starting point on the elliptic curve called G. Everyone knows this starting point. It is public information. Think of it as the yellow paint that both of you will use as your base. Step 2. Pick your secret numbers. Ephemeral means temporary. Here is where the term ephemeral comes in. It simply means temporary. You pick a secret number for this conversation only. Let's say you pick 5. Your friend picks their own secret number. Let's say 7. These are your private keys. After this conversation, you will throw these numbers away and pick new ones next time. It is like using a disposable phone number for each call. Step 3. Create your public colors. Now comes the clever part. You take the base color, yellow, and mix it with itself 5 times, your secret number. Your friend takes yellow and mixes it with itself 7 times. In ECDHE, this mixing is done by adding a point to itself on the curve. If G is our starting point, you calculate 5 times G, G plus G plus G plus G plus G, and your friend calculates 7 times G. These results are your public keys, new colors that you can safely share. Step 4. Exchange your public colors. You post your mixed color, 5 times G, on the public bulletin board. Your friend posts their mixed color, 7 times G. Everyone can see these colors. But here is the key. Simply seeing the final color does not reveal how many times you mixed. It is like seeing orange paint but not knowing if it is 3 parts yellow plus 1 part red, or 5 parts yellow plus 2 parts red. Step 5. The magic. Creating the same secret. This is the beautiful part. You take your friend's public color, 7 times G, and mix it 5 more times, which represents your secret number. Your friend takes your public color, 5 times G, and mixes it 7 more times, which represents their secret number. You both end up with the exact same final color, 35 times G. Why? Because 5 times the quantity 7 times G equals 7 times the quantity 5 times G, which equals 35 times G. It is like multiplication. The order does not matter. Use and destroy. You both now have the same secret color, 35 times G, that no one else can figure out. You use this to encrypt your messages. And then, and this is crucial, you both destroy your secret numbers, 5 and 7. Next time you talk, you will pick completely new numbers. This is what makes it ephemeral and provides perfect forward secrecy. Even if someone records your conversation and later discovers one of your secret numbers, they cannot decrypt old conversations because those numbers no longer exist. The eavesdropper problem is this. Someone watching sees yellow, which is G, your orange, which is 5 times G, and your friend's green, which is 7 times G, but to find your shared secret, which is 35 times G, they would need to figure out either 5 or 7. With elliptic curves and huge numbers, this becomes practically impossible, like trying to unmix paint. Popular curves and implementation. Not all elliptic curves are created equal. The choice of curve can significantly impact both security and performance. Let me guide you through the most important curves you will encounter in the wild and explain why certain curves have become industry favorites. The NIST curves, P256, P384, and P521, were standardized by NIST and have been widely deployed since the early 2000s. P256, also known as SEC P256R1 or Prime 256 volts 1, is by far the most common. It offers 128-bit security, which is equivalent to 3072-bit RSA, and is supported by virtually every TLS implementation. P384 and P521 offer higher security levels, but are used less frequently because of performance costs. However, these curves have faced some controversy. The constants used in their generation were not fully explained, leading to concerns about potential backdoors. While no vulnerabilities have been found, this uncertainty led to the development of new curves with verifiable generation processes. Curve 25519 and X25519. Created by Daniel Bernstein in 2005, Curve 25519 was designed with both security and performance in mind. Its design choices make it resistant to many implementation errors that plague other curves. X25519 is the Diffie-Hellman function on Curve 25519. It is incredibly fast, about 2 to 3 times faster than P256 on most platforms. Google, Cloudflare, and many others have adopted X25519 as their preferred choice. This curve is larger, offering 224-bit security. It is based on the same design principles as Curve 25519, but it provides a higher security margin for applications that need it. While not as widely deployed as X25519, it is gaining adoption in high-security contexts. Implementation considerations are crucial. Elliptic curve operations involve complex mathematics that must be implemented carefully. Side-channel attacks can leak private keys through timing variations, power consumption, or electromagnetic emissions. Modern implementations use constant-time algorithms and other countermeasures to prevent these attacks. The choice of curve often involves trade-offs between security, performance, and compatibility. For new applications, X25519 is typically recommended due to its excellent performance and security properties. For maximum compatibility, P256 remains the safe choice. Security benefits and perfect forward secrecy. Let's dive deep into why ECDHE is considered so secure and why perfect forward secrecy is such a game changer for internet security. Understanding these benefits will help you appreciate why ECDHE has become the cornerstone of modern secure communications. Perfect forward secrecy (PFS) is perhaps the most important security property that ECDHE provides. Here's a scenario to illustrate why it matters. Imagine a government agency or criminal organization is recording all encrypted internet traffic, hoping to decrypt it later. With traditional RSA key exchange, if they ever obtain the server's private key, through hacking, legal compulsion, or insider threats, they can decrypt all past recorded traffic. Years of communications suddenly become readable. With ECDHE, this attack fails completely, since new ephemeral keys are generated for each session and immediately deleted after use. Compromising the server's long-term private key does not help decrypt past sessions. Each session's encryption keys are mathematically independent. It's like each conversation uses a unique padlock that's destroyed after use. Finding the master key to the building does not help open old padlocks that no longer exist. The computational efficiency of elliptic curves provides another layer of security. Because ECDHE is so fast, there is no performance penalty for generating new keys for every connection. This means we can afford to use ephemeral keys everywhere, whereas with classic Diffie-Hellman, the computational cost often led to key reuse. ECDHE also provides strong security against quantum computers, at least for now. While quantum computers will eventually break current elliptic curve cryptography using Shor's algorithm, they cannot break the perfect forward secrecy property retroactively. Past communications protected by ECDHE remain secure even if quantum computers arrive tomorrow, as long as the ephemeral keys were properly deleted. Additionally, the smaller key sizes of ECDHE reduce the attack surface. Smaller keys mean less data to protect in memory, fewer opportunities for implementation bugs, and reduced exposure to side-channel attacks. The mathematical structure of elliptic curves also provides some inherent resistance to certain types of attacks that affect traditional Diffie-Hellman. Real-world deployment and performance. ECDHE is not just a theoretical improvement, it has been deployed at massive scale across the Internet. Let me show you how major organizations use ECDHE and share some real performance numbers that demonstrate why it has become the de facto standard. Google was one of the early adopters, switching to ECDHE for all their services around 2011. They reported that moving from 1024-bit RSA to P256 ECDHE actually reduced their CPU usage despite providing stronger security. Today, if you connect to any Google service, for example Gmail, YouTube, or Google Search, you're using ECDHE, most likely with the X25519 curve. Cloudflare, which handles traffic for millions of websites, has published extensive data on ECDHE performance. They found that X25519 ECDHE is about 20% faster than P256 ECDHE and over 250% faster than 2048-bit RSA for a service handling millions of requests per second. These performance improvements translate to significant cost savings and better user experience. In terms of actual numbers, on a modern server CPU, an X25519 ECDHE operation takes about 0.15 to 0.25 milliseconds. P256 takes about 0.3 to 0.5 milliseconds. Compare this to 2048-bit RSA at 1 to 3 milliseconds or 3072-bit classic Diffie-Hellman at 10 to 20 milliseconds. For mobile devices, the differences are even more pronounced due to limited processing power and battery constraints. The TLS 1.3 protocol, finalized in 2018, made ECDHE mandatory for all connections. This means that modern secure connections must use ephemeral key exchange. Static RSA key exchange was completely removed. The protocol also reduced the number of round trips required, making ECDHE connections even faster. Major CDNs and cloud providers have optimized their ECDHE implementations extensively. AWS, Azure, and Google Cloud all use hardware acceleration for ECDHE operations on their load balancers. Intel and AMD have added special CPU instructions, like ADCX/ADOX, that speed up the mathematical operations used in elliptic curve cryptography. Browser support is now universal. Chrome, Firefox, Safari, and Edge all support multiple ECDHE curves and prefer them over other key exchange methods. Mobile browsers benefit especially from ECDHE's efficiency, as it reduces both CPU usage and network overhead. Future of ECDHE and post-quantum considerations. As we look toward the future of secure communications, ECDHE faces both opportunities and challenges. The most significant challenge on the horizon is quantum computing, but the cryptographic community is already preparing for this future. Quantum computers pose a fundamental threat to all current public key cryptography, including ECDHE. Shor's algorithm can solve both the integer factorization problem, breaking RSA, and the elliptic curve discrete logarithm problem, breaking ECDHE, in polynomial time. Current estimates suggest that a quantum computer with around 2330 qubits could break P256 ECDHE. While we are not there yet, progress in quantum computing is accelerating. The good news is that the cryptographic community has been working on post-quantum replacements for over a decade. NIST is currently standardizing post-quantum key exchange algorithms. Leading candidates include lattice-based schemes like Kyber, code-based schemes like classic Michaelis, and isogeny-based schemes like SIKE, though SIKE was recently broken, showing how challenging this field is. The transition strategy is likely to involve hybrid schemes that combine ECDHE with post-quantum algorithms. This approach, already being tested by Google and Cloudflare, ensures security against both classical and quantum attackers. A typical hybrid might use X25519 plus Kyber 768, providing security even if one algorithm is broken. In the near term, ECDHE continues to evolve. New curves like SEC-P256K1, used in Bitcoin, and 4Q, developed by Microsoft Research, offer various improvements. Implementation techniques continue to advance, with new protections against side-channel attacks and faster algorithms for curve operations. The infrastructure for ECDHE is also improving. Certificate authorities now issue ECDSA certificates by default, reducing the data transmitted during handshakes. TLS 1.3's optimizations make ECDHE connections faster than ever. Hardware support continues to expand, with even low-power IoT devices now capable of efficient ECDHE operations. For developers and system administrators, the message is clear. ECDHE should be your default choice for key exchange today, but stay informed about post-quantum developments. The cryptographic agility built into modern protocols means we can transition smoothly when the time comes. Thank you for your attendance. Please consider subscribing to the channel.